Okay, thanks so much, Johannes. Yes, we're going to be looking at some joint work with Johannes and Toby, who's also here, looking at predictive processing, and more specifically the sort of subvariant known as active inference, and how we can study that from a categorical perspective. So, for those who aren't familiar with it, predictive processing is a sort of model of cognition that tries to be quite principled. It wants to be something you can apply at a very low level, say to a single neuron, or a very high level, like the whole brain or the whole organism, and to describe what cognition is at all these levels. And whenever I say predictive processing here, I'm talking about really active inference, which is this style developed by Carl Preston and his collaborators. So the basic ingredient here is that you have a system that comes with what's called a generative model, which is a model that has of how it's receiving observations from the world and explains these in terms of hidden states, the cause of these observations, and also how its own actions can influence these states of the world so that it can bring about things that it finds more desirable. And to do so, basically, it always does this with some form of Bayesian inference. So when it's receiving observations from the world and then interpreting that through inference, and this is called perception sometimes, and then it also carries out a form of inference to choose how it's going to act. And in active inference, the sort of key idea is that it can't really do this direct, like exactly. This Bayesian inference is very hard to calculate. So it does it by minimizing this quantity known as free energy, and this is the so-called free energy principle. And we'll see all these things come again throughout the talk to give these terms a bit more meaning. So the point about this rather than for category theory is that predictive processing, I'd say, is highly compositional in the way that it works. In particular, the generative models that you see in predictive processing are highly structured. So this is just a picture taken from one of their papers that just shows, just to illustrate the fact that it has all these different variables and components talking to each other inside the generative model. And this is why it works very well to treat them categorically and with string diagrams, which is what we do here. So this works about taking active inference, essentially predictive processing, and giving it a sort of succinct categorical formalization so we can get some clarity about what it is, and nice ways to talk about these generative models and all these things that the agent does. And the context is that it's carried out in this FGO diagram, looking at theories of consciousness with Johannes and Bob also and Harney, which was hosted at the Tull Institute. So very supportive of the work, and this is about, and so yeah, it kind of in some sense follows on from what's already been mentioned by Bob and Johannes, which is where we treated IIT theory of consciousness also in terms of these string diagrams, or the kind of process theories that Bob told us all about in the first talk. And in general, in the applied category theory community at the moment, there's various approaches to looking at related topics, I'd say, to predictive processing, including some stuff called categorical cybernetics, and lots of previous work that Toby's been doing as well in this area. Here's Toby. Oh, yes. Okay, so we should just start on the actual formalism now. So what you're doing all the time is looking at processes here. There'll be classical ones, so the probabilistic processes. So formally what we're doing is working in a monoidal category. There won't be a lot of category theory like mathematical notation because that's where we can use these string diagrams that I'll told us all about at the beginning of the day. So here the string diagrams are showing probabilistic processes. So I'm reading them bottom to top. So the objects, the wires, you can think of them as finite sets. They can be more general, but it's perfectly fine just to think of the idea that they're finite sets. And then this would be like a positive matrix from x to y, so you might write the entry something like this to suggest probability theory of it, m of y given x. In particular, a channel, we're often interested in channels, which are ones that are normalized, so they send each x to an actual distribution. So this is a process where you give it an input and it gives you an output according to some distribution on y. And we're in a monoidal category, so we can compose things, and that's the point. So the two sort of basic forms of composition would be plugging things together in a line, so we have something from x to y and y to z. Then the diagram is encoding what you would have to do in probability theory with a sum or an integral, so it's kind of nice that the calculations you do just get turned into simple diagrams here. If you run two things in parallel like this corresponds to really two independent probabilistic processes. And in general, as we saw, you can have diagrams where the boxes have multiple inputs and outputs. So you can have something like a probability channel here, where you can, can have multiple inputs x1 and xn, and these outputs y1s as well. And special cases then are things like probability distributions. So actual distribution is a special case of a channel just where there's no input. So if you see just a box with no inputs, it's basically a probability distribution. And we also use some extra sort of gadgets around in our category, which help you describe probability theory. So in particular, we have these copy maps on each object. I also have these processes for discarding a system, and they're very useful for talking about marginalization in probability theory. So you have something like omega here would be a joint distribution over x and y, but let's say we only care about x, so we marginalize out y. in the diagrams you just plug this in, but if you have to do it with equations, it would mean summing over y. So the structures that these copy maps and discard maps have together make them what's called a copy-discard category, and these are what I use in a general area of studying probability theory and string diagrams. So that we're working in one of these copy-discard categories. You could be, basically what I'm saying, these are just finite sets. We're working in this category prob, so it's kind of simple finite probabilistic setting. But they could be something a bit fancier. In particular, predictive processing, you can work with often Gaussian processes come up a lot, so you could be working this category Gauss, where, yeah, it's basically linear maps plus Gaussian noises added to them. But it's fine just to think about this finite setting for illustration. So that's all just the general setup of how you treat probability theory in the diagrams that we'll see throughout the talk. Some stuff that's more particular to predictive processing now are the generative models themselves. So in predictive processing you have some agent, and it has one of these generative models that it uses to relate, as we said, states of the world and the observations it receives to these actions it can carry out. So the normal way they formalize this is with various notions of a probabilistic graphical model. I'd say sort of the most direct way would just be say it's a Bayesian network. So the normal definition of that would be that you do what's called a DAG, a directed acyclic graph. So you have a load of variables and you have some relationships between them that you draw in this DAG. And then you have a probability distribution that's compatible with that, and that's what you'd say and this DAG lets then talk about the compositional structure. If you actually look in the active inference books and stuff, though, they seem to be kind of slowly converging on using string diagrams, essentially. So this is the kind of Bayesian network they actually would draw all the time. Yeah, it's the model they would use, and they kind of want to do things like label these processes, and as well as the variables themselves. And so they're kind of converging on using string diagrams, I think. And that's because they are a natural thing to use. So the nice result is that there's a close correspondence between DAGs and as a result Bayesian networks and a certain class of string diagrams in these copy-discard categories. So the details of the kind of diagram don't matter too much, but there's something you can call a network diagram. The key point is that it's built from all these boxes that just have one output, multiple inputs, let's say, but only one output, and also copying and discarding. And what you can do is you can take a DAG and equivalently represent it as one of these string diagrams. And now a Bayesian network is about taking the DAG and giving it a kind of probabilistic interpretation, so basically a lot of probability channels. And so a Bayesian network amounts to drawing your string diagram and then filling in actual probability channels for all the boxes. So just an example here, we've got this DAG of x1, x2 up to x4, and I have circled x2 and x3 to say these variables are observed and the other two would be hidden. And in the string diagram what you do is you put each variable in as a wire, and you have a box that is like the mechanism which produces that variable in terms of its parents in the DAG. So this box C corresponds to x2, so that produces an x2 here. And the x1 and x4 are the parents in the DAG, so they go in as the inputs. And because x2 and x3 are observed, they end up as outputs in the network diagram. And the other ones wouldn't enter as outputs. And then, yeah, to specify the Bayesian network means specifying all these channels, so you have to give this prior A over x1, B over x4, and these two channels C and D. And if you're just looking at this, it's basically a way of describing a distribution. So this whole thing has no inputs, right? So it's a distribution over x2 and x3 that decomposes in terms of all these channels. And we can, what's kind of natural categorical is just to drop this idea of not having any inputs, and so go beyond distributions to probability channels in general. So the kind of building blocks of generative models from the categorical perspective are what we call open generative models. So this is just a slight generalization, and we're letting it now be defined in any one of these CD categories. So now we just start from the diagram. So we just say we're given one of these network diagrams, and an open generative model is given by the string diagram, and then giving it an interpretation in the category. So that means like saying what actually are all these objects. It's not just a picture, it's actually like corresponding to actual objects in your category and actual channels for all the boxes. And I would call this an open generative model. Open kind of referring to the fact that it can have inputs now. And it will be closed if it doesn't have any, and that corresponds to the previous type of generative model we've seen. And again, we can talk about observed variables being the outputs of the diagram, but now we can have inputs as well as the hidden ones. So the formula is what we're using here. It's just these network diagrams with these interpretations of category. It's actually just the same thing as what you used to describe causal models in general. So we've had some work with Robin Lorenz looking at causal models in string diagrams, and these generative models are basically a special case of that, or they're kind of the same thing, formally speaking, but they're used in this particular context of these agents in cognition here. So the building block of these open generative models, and now we're just going to see lots of examples. So the simplest kind of generative model, right, is you just have two things. It's not really compositional. You just have some observations living in this space, O, and you have the hidden states. So these are like, the observations can be images, like pixels, and the states are like your view of what's actually happening that's causing you to see this object, so representation of what's actually in the image. And the network diagram is just this picture, so there's no copying needed even. It just says, you know, S isn't an output, but S is hidden. O is an output, so that's the observed thing. And all we have is this prior distribution over the hidden states that tells us which states we think are likely. And this channel C equals the likelihood. And that says, you know, given this particular state of the world, what observations would we be likely to see? So most of the time, this is like a simple form of a generative model, just like the observed stuff and the hidden stuff. And when people talk about these, normally they often kind of talk about it via this distribution that you would get, which you can also describe in the string diagrams. It's basically the joint distribution over hidden states and observations, so like which ones are you likely to see together. And in the diagrams it just amounts to making S an output now by copying it out. So you have your prior go in, you copy it out, and then you run the channel on this. Now it'll give you this box that I just call M in a slightly different font, but just to say this is the joint distribution that's given by this model. So if it was just like this, we wouldn't really need all the categorical stuff, but in predictive processing they're not, they're normally much more structured. So this is an example of the kind of model you see a lot in active inference textbooks, things like that. So it would be, yeah, let's just read it through. Remember the diagram's going from bottom to top. So it'd be a discrete time model here, where you're looking at some system that has these hidden states, S1, S2, up to Sn. So there's n time steps. And at each time step it's getting some observation, O1, O2, up to On. So they kind of think about, yeah, systems with these discrete time models of what they're seeing. They use this kind of model. And there's all these channels going on, right? So the A channels are what are the hidden states causing observations at each time. And then there's transition channels that are telling you how the hidden states change over the time. So let's say given the state at some time, the state at the next time that the probabilistic channel determines that in terms of that one. So the state the next time is determined by the previous time, and also this extra variable, which I haven't talked about yet, and that's P. So P is short for policies, or action policies. So these are the way the system is modeling its own behavior. So you can think of one of these P as a behavioral policy of the system. So like here it could just be a sequence of actions, but it could be a kind of high-level variable describing what kind of actions the system's going to take. So given the way it's acting and the state of the world, the next state is determined with some probability, and that in turn determines what observations you see. And to make this a closed model, priors over the policies, so this habits thing. So this is saying what are the most likely types of action that I'll have, like the multiplying prior over how I'm behaving here. So this is the way that one of these models is represented in the string diagrams. And then the other important thing you can see about an active predictive processing is the notion of a hierarchical model, and it's also very nice to treat very diagrammatically. So basically a hierarchical model is given by getting a load of these open models and plugging them together in this sort of layered structure. So because I'm reading bottom to top, it would actually be the bottom Y would correspond to an actual high-level variable, confusingly, but it'd be like the object that's the cause of what's going on, let's say, or the overall view of what's happening. And then at the top it might be individual pixels or something. Or it could be like time, there could be different levels of time going on as you read up the model, so it could be quite slow features here, and then you have sort of more wires at the top because these are like individual fine-grained features of this model. So you often imagine in predictive processing that you've got something like in the brain there's these hierarchical models being constructed by plugging together these different layers to give the overall generative model. So that's just all of that's just been talking about generative models so far. What do you actually do with them in predictive processing? So most of the time we'll say, you have some fixed model of the world, and here we'll just think about the simple one with just some states, some observations. And then in some sense you receive an observation from the world, and you want to use it to alter your beliefs about what states are likely, because you're trying to say which ones explain the fact that I just saw this thing. So we can actually talk about this by just talking about this joint distribution M over S and O. So this this joint thing, and receive observation, which would now be in general fuzzy, so it's not like a point of O, it's a distribution over likely things in our observation, and we want to update the marginal on S, which would normally be our prior beliefs about what states are likely. We're going to update that in light of this observation. And there's a lot of work in category theory about how you do this. Normally, in predictive processing, there's some kind of Bayesian inference, and that's been treated rather in categorical in various places. So Bob and Rob had this paper from a while ago on picturing classical and quantum Bayesian inference, and there's more recent stuff going on in applied category theory and treating Bayesian inference in string diagrams. And one thing that comes out of that, I think, that's interesting is that there's actually multiple ways that you can do this that all make good sense. So I just talk about these two types that Vahyakov has written about as well. So you, firstly, what you could do, you receive your observation, so it's distributions, it's a fuzzy kind of thing. You're like, I think I saw this kind of thing, but there's some distribution to it. And you want to update your beliefs. You do that, one way is to compute this Bayesian inverse channel, which you can represent in string diagrams like this. So it basically means, take O, turn it into an input, and this dash box means normalize everything so that this is an actual channel, this box now. So you plug the observation into that channel. The channel you can think of as the Bayesian inverse telling you for each particular observation what states are likely to have caused it, given the model. And so you just sort of sum over all this distribution over here. The other option is to actually take your model, plug the observation into it directly, and then normalize everything. And it could be possible to miss these things, but when you're doing things in the diagrams, I think it makes them so simple to see that it becomes clear that there's at least these two good ways of carrying out updating. Often in the literature, people only talk about these these sharp observations, rather, in which case they both just coincide with the thing that you would normally call Bayesian inversion. But the other thing that's important about them is just that they are basically intractable. So there's these two good options, they're both there, but then you can't actually compute either of them. They both involve a lot of summations, or in the continuous case, there'd be a lot of integration going on here over these variables. So the point in the active inference is to try and find some way to compute something that you can actually calculate to approximate these updating processes. And you can do that through this quantity called free energy. I don't think I'd have time to go into it that much, the way that it works, but roughly, I'll just say, given two distributions, Q and M here, or thinking of Q as a kind of approximation of M, the free energy is this way to measure the kind of how close you are in your approximation to the original one, so it's a sort of distance between them as close to a KL divergence. The way that it's used are in these two ways in active inference. The first is called the variational free energy. So what's going on? You have your model, and you have an observation O that you receive, and you're trying to approximate this Bayesian inverse of the model relative to O, which you can sometimes denote with this dagger. So you can do that, in fact, as shown by minimizing this quantity, the free energy between these two. So this is saying, Q would be what states are now likely given this observation, and the pair of those together would be the free energy between that and the original model. That's the thing you're minimizing. This is called variation of free energy, and loads of the active inference literature, and it's about the free energy principle and about minimizing this quantity. But the arguments are quite hard to follow, so we've been trying to convert free energy to just these simple expressions to compare it, and in particular compare it to this other quantity that comes up called expected free energy. So this is what you do when you're talking about future states rather than current states. And I don't think the details matter too much here, but the point is just that it's another quantity you calculate in this free energy that allows you to do approximate inversion. But the interpretation now is that you've got a model about your actions and about future outcomes, future observations, and you have some preferences, which are often called C, to the future. And you can basically approximate how well your model is going to fit these preferences by minimizing this quantity. So if you want to know how well you're doing, you can calculate this expected free energy quantity. So these will just come up a bit in some of the diagrammatic stuff now that I'll do in the last part of the talk. So the aim now of doing all of this is just to lay out all of the basic ingredients of what goes into active inference and predictive processing in terms of the process theoretic language. And now we'll just look at active inference itself and try and get a diagrammatic picture of what it is. So active inference is this idea of how an agent can have a model of the world and its own actions, and then it updates its view of what's going on in the world and how it should act both using inference. So you have this model, which we can view as basically a 2-time step version of the one I showed before. So you just have some notion of the states and observations in the current time, and some notions of the future states and future observations, and how your actions given by these policies are affecting both of these. So you get actions will influence the state and the future state. And you have your typical behaviors, which you might call habits here. And then again, we're having receiving something that we want to do approximate Bayesian and updating over. So what happens is we have these preferences again, C, about the future. And we also have an observation that we get in the present. So we just see something happening, and we know what we want to happen in the future. And now what we can think of this as doing now is we want to choose our action through inference to explain this in some sense. So we're saying, given that I've got this observation now, and I know I'm just going to get my preferences in the future because I want to, so I'm just going to assume I do, then you do Bayesian inference over that, and that tells you if that's happening, well, what's the likely course of action I'm taking. So how should I behave in order to explain this and obtain these preferences. And then in the literature, you'll find that they just give this formula in terms of free energy for how you can do this. But the way that they derive it is quite hard to feel it's really precise and something else. I think it's fair to say they use the they talk about it doing the EFE as a prior or something like this, and then doing the VFE, which is quite weird because it's not really a prior. So we wanted to see how you can get this formula out from the structure of the generative model instead, and whether the diagrams would help make sense of this. So I obviously won't be able to go through like a proof in detail here, but you'll just see some diagrams moving around to show how, from the structure of that model I showed before, you can end up with this kind of formula coming out. So if we think of what we said we're doing, we've got this model that our P is our policies, so actions. We've got our observations, and we've got stuff about the future here. And we're trying to update, given O and given this observation, and given our preferences. And updating, one of the forms of updating is showed like this. So we plug them in and then we normalize. That's what we'd like to do, but we're only going to be able to approximate it. So let's just take this part of the picture now. Given the structure of the model we had before, you can just take it from me. What you can do is rewrite it in this way. It basically just says there's this part of the model that relates to the current time. So you've got the current state, your current observation, and then you've got the part relating to the future bit. So we rewrite it in this way, and then as a result we split it into these 2 steps. This is what they do in the active inference books, but it's kind of all just coming out from the diagrams here. So we look at the current time part, and we want to basically approximate this bit, and you do that through approximate inversion. So you basically use a step where you approximate this using this variation of free energy thing. So roughly each policy goes in here, you calculate this this Q like we had in the pictures before, but now for each policy, so that it has this P input as well. So this is an approximate inversion. So you're carrying out approximate inversion for each input, and also multiplying by its PFE. And you can show that will be approximately equal to what we have there. And this step's often called perception. This is that step of you're just talking about, you've got an observation and you want to infer the hidden state. So you start with doing that first, free energy quantity. Next you have the top part of the picture. Okay, we just collapse it together into one thing. And now this is like a model for each policy that goes in here. We have this model saying, it basically gives us now what we'll expect to see in the future. And we're basically trying to see how closely that fits with these preferences here. So we want to approximate this thing. And that's what that expected free energy quantity I mentioned does. So you just, for each policy, you'll calculate that. So overall, you end up with this as the picture. And if you see what this is now, this is actually the expression we have here. So because of these exponentials going on, and we're normalizing it, it comes out as a softmax type expression. So basically, it's a formula that says, if you want to do this kind of policy updating by inference, to choose how to act, like by Bayesian inference, you should do it by this step that involves thinking about your prior, about how you normally act, and these variational free energy and expected free energy quantities. And then you take this formula just reading off from the pictures. This is summarize what we've seen, and basically try to lay out how the ingredients that go into active inference can be nicely explained in process theories and these string diagrams and model categories. So generative models corresponded to these Bayesian networks, and it's known that they correspond to a class of string diagrams. Bayesian updating has also been studied quite a bit, and we talked a bit more about that. And Jikla picked out these 2 different forms. And the main application was then taking all that machinery and looking at active inference and just seeing how you can treat experiments as a whole and picture it's kind of 2 steps of perception and planning, just at the string diagram level. There's loads more stuff we could do here that would be nice to do in future. So everything I said so far was just, oh, you minimize free energy. I didn't even say how you do that. It's done with these algorithms called message passing normally. That would be good to be able to treat the diagrams in some way. There's also questions about how sort of local or compositional this whole property of minimizing free energy is that we'd like to be able to say a bit more about. There's a question of what happens with these two different types of Bayesian updating I mentioned. They just said those two types. I used one of them in the derivation, but it would be interesting to think about what's the most natural, I think, from the perspective of free energy and predictive processing. And I didn't even say anything about consciousness, right? So the theory is just a framework of cognition. There's all sorts of ways that people would like to relate it to consciousness, which is why it's of interest to this community, but we didn't talk through explicitly what those look like in the formalism, so it would be very nice to do that in the future too. And also maybe we can relate it to these other theories of consciousness, such as IoT and G&W, because you can, as was mentioned, you can kind of cast them in process theories, and also even IoT kind of starts from the same setup of these classical probabilistic processes in some way. But that's it for me, yeah. Thank you.
So we have time for a few questions. Go ahead, please, yeah.
For the message passing and local free energy, you're talking about beta free energy, right?
What, sorry?
Beta free energy. No?
Beta?
Beta, like when you do, so basically when you enter into the graphical model, you're thinking about beta free energy, or are you thinking about something more general?
I think you're using technical terms, I don't know, basically.
So basically when you have entropy, and if you look at the DAG, you can decompose entropy as sum of local entropies, and then you just add a combinatorial factor that is given by Mobius inversion and process. So you just do an inclusion-exclusion formula on entropy.
Okay.
And so this defines, in fact, entropy for local systems. But the thing is, so this is known, it's called the beta free energy, which is the variational free energy for belief propagation.
Okay.
So, is it what you're referring to when you're talking about local free energy? Because in fact, there are some real problematic foundations around it.
Okay.
Like, and there, so there's
no, I think we should talk about it more. Yeah, I think that's interesting. It sounds like it's the same. It's the same sort of direction.
Okay.
It's about saying, can we view? I mean, ideally, you have all these components, like in the brain or something. They're even meant to be different regions in the brain, right? And you want to say that each of them is minimizing free energy itself, and also that the whole thing is minimizing free energy.
Yeah, but that's yeah.
And like
problems here.
Yeah. Yeah, in a good.
So did you? Okay, so because you did.
Maybe let's take that to the coffee break. We don't have.
No, this would be good.
Yeah. So, Camilo, would you like to come up already and set up everything, and then we have two more questions, maybe? Now it's pointing. Yeah, go ahead.
I mean, so von Neumann kind of simplified quantum theory and put it in a solid mathematical form in some way. Let's say. Do you see yourself as doing the same thing for this theory? Do you see some structure that you capture better with this mathematical formalism that is not so well describing Friston
very
more
broadly? Yeah. I'm not going to say I'm doing von Neumann, but I mean, I think that the string diagrams are actually like the most natural way to handle causal models, so predictive models, because they want to draw the diagrams on these papers, they draw diagrams for the model, but then everything else is sort of separate. People want to use graphical models for these. And the nice thing on the string diagrams is that the probability theory stuff and the representation of the model are happening in the same formalism. So it's actually a natural, it's not just like taking some categories and applying it for the sake of it. It feels like a natural way to do it. Yeah.
And Friston, what kind of what he does? I mean, what is more end wavy in the Friston theory that in your
This was essentially about translating the Friston style stuff, I would say. So there's not anything.
I think to have so people from the UK, they're so extremely polite. So when they say it's hard to make sense of, they mean it's complicated.
Okay? Exactly. That's
okay. Yeah. So if you mean the active inference formula part, I basically wasn't convinced by the way that you write the formula.
Right.
And I think that is more transparent because you have the model and you see how that is in fact an approximation to what you want to do, and you just start with something elementary of I have the model, I want to update with this observation and preferences in this case, and that's it. And that's the kind of principle thing they want, right? They want to just be like applying one type of Bayesian principle, and so everything else falls out just from the structure of the model, but you don't have to keep adding more details. So the hope would be that it looks like that. if it ends up different to what they did, that's fine too.
So I think the analogy of phenomenon is really good actually, in terms of the status of quantum theory before he did that. That's comparable. Yeah. Last question? Yeah, go ahead, please.
It would be nice to use maybe this kind of formalism to kind of translate the adversarial collaboration between this IIT and the predictability and the GMW prediction and particular experimental setup, because you have take a look at their proposal of the comparing the experimental prediction. It's very hard to understand why this is the kind of prediction from each theory. But if you have this kind of formal diagram to simplify their theory and the prediction, that would be great.
That would be great. Yeah, I agree. That would be really nice. I think by IT it's very hard to get from the structure to the predictions. Like it would be nice if they just start from the process series. And we could try it a little bit more now. The other two would probably be easier to do that, I think. But it would be great, yeah, to have them. That's one of the hopes of putting them in this. They're more than process theory or string diagram language, that you can then compare them more. So it would be great to demonstrate that, yeah.
Okay, let's give another round of applause.